Two massive storm systems are closing in on each other right now, and what happens next could rewrite everything you thought you knew about dangerous weather. This is not a drill. This is not an exaggeration. When two big storms collide, the atmosphere does something violent, something unpredictable, and something that has killed thousands of people throughout history without warning. So before the next major collision event hits, you need to understand exactly what is coming, exactly why it happens, and exactly why it is far more dangerous than either storm alone. Let's start with something that most people get completely wrong. When you hear that two storms are approaching each other, the instinct is to think one will weaken the other. After all, if two forces push against each other, they cancel out, right? That is not what happens in the atmosphere. In fact, the opposite is often true. When two storm systems interact, they can feed each other, steal energy from each other, and in the most extreme cases, they can merge into a single monster system more powerful than both combined. Meteorologists have a name for this process. They call it the Fujiwara effect. And once you understand what it means, you will never look at a two-storm forecast the same way again. The Fujiwara effect was first described in 1921 by a Japanese meteorologist named Sakuhei Fujiwara. He noticed something extraordinary while studying water vortices in a laboratory. When two rotating vortices come close enough to each other, they do not simply collide and stop. They begin to orbit around a shared center of mass, like two dancers locked in a gravitational pull. They circle each other, drawing closer and closer until one of three things happens. The weaker vortex gets absorbed completely into the stronger one. Both vortices merge into a single combined system, or they interact briefly and then separate, but both are changed, sometimes dramatically, by the encounter. What Fujiwara observed in a laboratory tank of water applies almost perfectly to tropical cyclones, hurricanes, and large extratropical storm systems in the real atmosphere. The physics does not care about scale. Vortices behave like vortices, whether they are 6 inches wide in a science experiment or 600 miles wide over the open ocean. Now here is where it gets frightening. When two hurricanes or two powerful low-pressure systems begin the Fujiwara dance, the first thing that becomes almost impossible is forecasting. The track of each storm becomes extraordinarily difficult to predict because each system is simultaneously influencing the steering currents that guide the other. Normally, a hurricane is steered by large-scale atmospheric flow, the jet stream, high-pressure ridges, and trade winds. But when a second vortex enters the picture, it creates its own local steering influence. The two storms pull at each other. They can make sharp, unexpected turns. They can stall in place for days when they should be moving. They can accelerate when forecasters predicted slowing. Every rule that normally governs storm movement starts to bend. And in a scenario where people need to know whether to evacuate, whether to shelter, whether to prepare, that uncertainty is not just inconvenient, it is deadly. Let's talk about real history, because the record books are full of moments when two storms colliding produced catastrophic results. One of the most studied events in modern meteorology occurred in October 1991, and if you know anything about weather history, you already feel a chill at the date. That was the month that gave us what Sebastian Junger would later make famous as the perfect storm. What most people do not fully understand about that event is that it was not simply one storm. It was the collision of three separate weather systems. A dying hurricane, Grace, moved northeast and collided with a massive extratropical low-pressure system that was itself strengthening explosively. The energy transfer between these colliding systems was violent and rapid. Wave heights in the North Atlantic reached 100 feet. The fishing vessel Andrea Gale and her crew of 6 were lost to those seas. But here is the meteorological detail that should shock you. The storm that formed from those colliding systems was so anomalous, so strange in its behavior, that it briefly re-intensified into a tropical storm, then a hurricane, even as it was technically dying. Colliding storms can resurrect dying systems. They can inject new life into something that should already be weakening. Go further back to 1992, and you find another catastrophic example. Hurricane Andrew made landfall in South Florida as a Category 5 storm. But in the days before landfall, Andrew's track was dramatically influenced by an interaction with an upper-level trough, a separate atmospheric disturbance that effectively steered Andrew southward and southwestward directly into the most densely populated part of Dade County. Had that upper-level system not been present, Andrew's track shifts suggest it could have made landfall well north of Miami. The collision of Andrew's circulation with that trough did not weaken Andrew. It guided it with pinpoint accuracy into the worst possible location. That is the terrifying subtlety of storm interactions. One system does not have to merge with another to cause disaster. The mere gravitational pull between them, the way one influences the steering of the other, can be enough to turn a bad situation into a historic catastrophe. Now let us talk about what actually happens inside the atmosphere when two storms collide, because the mechanics are extraordinary. Every storm at its core is a rotating column of air. A hurricane rotates counterclockwise in the northern hemisphere. An extratropical cyclone does the same. That rotation is driven by a pressure difference, warm, moist air rising in the center, cooler air sinking at the edges, and the Coriolis effect from Earth's rotation spinning everything into a vortex. When two such vortices approach each other, the rotation of each one begins to interact with the wind field of the other. On the side where both systems' winds are blowing in the same direction, those winds add together and become significantly stronger. On the side where the winds oppose each other, they partially cancel out and create a zone of chaotic, unstable, violently turbulent air. That zone between two colliding storms is often the most dangerous location to be. It does not feel like the eye of a hurricane. It does not have the clear signals that emergency managers use to trigger evacuations. It can look like ordinary severe weather right up until the moment it becomes extraordinary. The rainfall that two interacting storms can produce together is another factor that deserves far more attention than it gets. Each storm system brings its own moisture reservoir, its own pipeline of water vapor pulled from the ocean surface or from warm continental air masses. When two storms collide and slow each other down, or when one wraps around the other and stalls, all of that moisture gets dropped in the same location over an extended period of time. This is how rainfall disasters happen. This is how a region that might expect 6 inches of rain from a single storm event ends up receiving 30 or 40 inches over 48 hours. The 2017 Hurricane Harvey disaster in Texas, while not a classic two-storm collision, demonstrated exactly this principle. Harvey stalled because of competing atmospheric systems that effectively blocked its movement. The result was catastrophic, historic flooding that submerged entire neighborhoods under feet of water for days. Now, imagine that stalling and that moisture being doubled by a second storm pumping additional water vapor into the same system from a different direction. The math becomes almost incomprehensible. Let us talk about what happens when two storms collide and one of them is already a major hurricane. This is where the Fujiwara effect moves from fascinating to terrifying. In 2020, two named storms made landfall in Central America within 2 weeks of each other. Hurricanes Eta and Iota both reached Category 4 strength and struck Nicaragua and Honduras within days of each other. The two storms were not a classic Fujiwara merger, but they interacted. Iota's development and track were influenced by the atmospheric disruption left by Eta. The ground was already saturated from Eta's catastrophic flooding when Iota made landfall. The result was among the worst humanitarian disasters in Central American history. Over 200 people were killed directly. Hundreds of thousands were displaced. Entire communities were buried under mudslides triggered by ground, so saturated from the first storm that the second storm only needed a fraction of its normal rainfall to trigger catastrophic landslides. Two storms do not have to merge to multiply each other's deadliness. They simply have to arrive in sequence, close enough in time and space that the damage from the first one removes all the natural defenses against the second. There is another phenomenon associated with colliding storm systems that almost never makes headlines but is extraordinarily dangerous, and that is the rapid development of tornadoes in the interaction zone. When two storm systems are pulling air in different directions at the same level of the atmosphere, they can create extreme wind shear conditions, meaning wind speed and direction change dramatically over very short distances. Wind shear is the single most important ingredient in tornado formation. It is what allows a thunderstorm's updraft to begin rotating and eventually tighten into a tornado. In the boundary zone between two colliding large-scale storm systems, wind shear values can exceed anything that a single storm would normally produce. Tornado outbreaks have occurred repeatedly in history along the interaction boundaries of colliding storm systems. The April 2011 super outbreak, the deadliest and most destructive tornado event in modern American history, occurred when a powerful upper-level disturbance and a vigorous surface low-pressure system combined forces across the Deep South. Over 350 tornadoes were confirmed. 321 people were killed in a single day. That event was not caused by two tropical storms colliding, but it was fundamentally a two-system interaction event, an upper-level vortex driving energy down into a surface vortex, both systems amplifying what each one could have done alone. Here is a fact that should stop you cold. The National Hurricane Center and global meteorological agencies use computer models to forecast storm tracks and intensities. These models are extraordinarily sophisticated, drawing on satellite data, ocean buoy measurements, aircraft reconnaissance, radiosonde balloon data, and decades of observed storm behavior. They are genuinely impressive tools, but when two storms interact, the error margins in those models expand dramatically. The track forecast uncertainty cone, the cone of probability that shows where a storm might go, grows significantly wider during interaction scenarios. Meteorologists openly acknowledge this. When two systems are dancing around each other in a Fujiwara interaction, the models sometimes disagree with each other by hundreds of miles on where the resulting storm or storms will go. Hundreds of miles. In hurricane forecasting, hundreds of miles is the difference between a major metropolitan area taking a direct hit and a major metropolitan area experiencing a near miss. It is the difference between life and death for people deciding in the hours before landfall whether to stay or go. The ocean plays a role in two storm interactions that adds yet another layer of danger. When a hurricane passes over open ocean, it churns the water beneath it. It pulls cold water up from the deep in a process called upwelling. The cold water acts as a natural brake on the hurricane because hurricanes need warm water to maintain and intensify. Normally, a single hurricane is somewhat self-limiting in this way. It weakens the oceanic fuel source beneath it as it moves. But when two storms are in proximity, something different can happen. One storm can churn and mix the ocean in a particular area, and then the second storm arrives before the ocean has had time to restabilize. Depending on the depth of the warm water layer, this can either leave the second storm with a depleted fuel source and weaken it, or it can create a situation where the mixing has actually brought up a slightly warmer subsurface layer in some regions, giving the approaching storm unexpected fuel. Ocean heat content during two storm scenarios is one of the most actively researched areas in modern hurricane science, precisely because we still do not fully understand all the ways the ocean responds to sequential or simultaneous storm stress. Let's bring this closer to the present and talk about what the data is showing us about two storm events in a warming climate. Ocean temperatures are rising, not slightly, significantly. The surface layer of warm water available to fuel tropical cyclones is deepening. This matters enormously for multi-storm interaction scenarios because it means that the self-limiting upwelling effect, the natural brake on hurricane intensity, is becoming less effective. A warming ocean means storms can remain at dangerous intensity for longer. It means that when two storms enter an interaction scenario, both of them are drawing from a richer, deeper fuel source than storms of previous generations did. The atmosphere is also holding more moisture because warmer air holds more water vapor. That directly translates to more extreme rainfall potential from any storm event, and in a two-storm scenario where rainfall is being doubled, tripled, or concentrated by the interaction dynamics, the flooding consequences escalate accordingly. Scientists who study extreme weather events have identified a deeply concerning trend in recent decades. The number of rapid intensification events, storms that gain hurricane strength or intensify by 35 phenotopility or more in 24 hours, is increasing. Rapid intensification is already the single hardest thing to forecast accurately. It catches coastal communities off guard. It causes evacuation orders to come too late. Now combine rapid intensification with a two-storm interaction scenario. Imagine two storms that are already difficult to track because of their Fujiwara dance, and then imagine one or both of them suddenly undergoing rapid intensification in the 24 to 36 hours before landfall. That is not a hypothetical nightmare scenario. That is something that the historical record shows has already happened and will happen again. The only question is where and when. Emergency management professionals who deal with multi-storm scenarios describe them as the events that keep them awake at night more than any other weather type. A single major hurricane is terrible. It is destructive and deadly and demands enormous resources and coordination. But the playbook exists. The models for evacuation, resource prepositioning, shelter management, and emergency communication are well developed for single storm events. Two storm interactions break the playbook. Resources that are prepositioned for one storm's expected track may end up in the wrong location if the interaction causes an unexpected turn. Evacuation orders that are issued based on current track forecasts may be issued for the wrong zone if the Fujiwara dynamics shift the point of maximum impact. Search and rescue teams that are staged in one area may find themselves cut off by flooding from the other system. Multi-storm scenarios require a kind of multi-dimensional thinking and coordination that emergency management infrastructure is still actively trying to build. The most important thing to understand as you watch two storms closing in on each other on a weather map, as you see the headlines and the warnings and the forecast tracks, is that the uncertainty is not a failure of meteorology. It is an honest representation of physical reality. Two colliding storm systems are genuinely unpredictable in ways that a single storm is not. The atmosphere at those scales is chaotic in the mathematical sense of the word. Small differences in initial conditions produce dramatically different outcomes. Meteorologists are giving you their best science. They're being honest with you when they express that uncertainty. The correct response to that uncertainty is not dismissal, not reassurance that maybe it will miss, not waiting for a more definite forecast before acting. The correct response to two-storm uncertainty is to treat the worst-case scenario as the planning scenario. Prepare for where these storms could go at the extreme edge of their forecast uncertainty, not for where the centerline says they are most likely to go. Because here's the final and most important fact about when two big storms collide. The atmosphere does not care about averages. It does not deliver the mean outcome. It delivers whatever the physics produces on that specific day with those specific conditions. And when two massive rotating systems are locked in their gravitational dance, trading energy, bending steering currents, saturating the atmosphere with moisture and instability, the physics can produce something extraordinary, something the models did not fully capture. something that arrives faster, stronger, and wetter than anyone expected. History proves this again and again. The storms of record, the events that fill the history books and the disaster registries, are disproportionately the events that involved multiple interacting systems. The perfect storm of 1991, the 2011 super outbreak, the compound disasters of Eta and Iota. These were not freak accidents of bad luck. They were the predictable result of what happens when the atmosphere combines its forces. Two big storms are closing in on each other. Watch them carefully. Respect the uncertainty in their tracks. Do not wait for certainty that may never come before acting. And understand that what you are watching is not just two weather events. It is the atmosphere gathering its full power into something that may be unlike anything that has come before it. The time to prepare is not when the wind begins to howl. The time to prepare is right now, while the choice is still yours to make.